He kōna ipurangi tēnei nā te reo irirangi o Aotearoa.
They say life is stranger than fiction.
So, a black hole is almost a memory of where material was in the universe, almost like a belly button in the fabric of space. And the bigger stars, nothing will stop their collapse. There's no force known in nature that stops them from collapsing to a point.
But sometimes what we see in movies or read in books is so incredible that it obviously couldn't be possible. Or could it?
The surface of the black hole isn't kind of painted on space, if you like. You could make your way across the event horizon without really noticing that it was there.
Welcome to Sci-Fi Sci-Fact. I'm Brian Crump, and this is a podcast where we take science fiction's strangest ideas, weirdest elements, most unfeasible plot drivers, and explore if they could actually happen in real life. Maybe they already have. And in every episode, we bring in a scientist from New Zealand's MacDiarmid Institute to explain the theories behind some of fiction's more fantastic flights of fancy, if any theory exists. In this episode, Richard Easther, theoretical cosmologist and professor of physics, head of the department, in fact, at Auckland University, crosses the event horizon to give us his scientific take on the black hole from the movie Interstellar.
Approaching the event horizon. Port side, dipping down beneath it to go through it. Heading towards blackness. I'm visual even. It's all black. Charles, do you read me? It's all blackness.
Well, let's begin with that first question. Wouldn't you be crushed by the gravity if you went inside a black hole? Wouldn't that be the end of that scene in real life?
It depends how big the black hole is. And so it's not so much that you're crushed as that you're stretched. And so if you approach if the sun turned into a black hole and you approach that, then the gravity gradient is so intense as you approach the small black hole that, your head might be accelerated faster than your feet. And that leads to a process that's known technically as spaghettification, that you get longer and longer and longer as you fall into the black hole. In the case of a really big black hole, though, the gradient of the gravitational field as you approach the event horizon, at least in principle, is shallow enough so that you would be able to make it across. And this, in the movie, this is a very big black hole. It's 100 million times the mass of the sun.
Okay, it is the planet, or the black hole, it's not a planet, of course. The black hole is called Gargantua, I think, isn't it?
I think that's what they call it, and it's so this is what we call a supermassive black hole, and we believe that objects this big reside at the centre of galaxies. There's a 4 million solar mass black hole at the centre of the Milky Way, and 100 million solar masses is in some galaxies is what you find there. So that part of it seems to be real, seems to get the tick.
Well, let's just remind people what a black hole is. It's something which is has such massive gravity that not even light can escape it, right?
Yeah, that's pretty much exactly what it is. That idea that light has, once you realize that light moves at a finite speed, you say, well, I can't throw a ball into the air on the Earth and have it run off into space, but if I was on a small asteroid, I could easily chuck a ball in a way that would make it never come back. And so, light is the fastest thing we know how to throw, and if you make the gravitational field intense enough, then not even light would escape. And that was an idea that was had back actually in the 1780s. And then Einstein's work on general relativity in 1915 produced solutions to his equations that give us the sort of modern theory of the black hole that we have today.
How are black holes formed?
That's a good question. So I've already given, I guess, part of that away is that big stars, when they die, they reach a point where they run out of fuel. So the sun doesn't collapse because it's burning at its centre, and that provides an outward force that works against the force of gravity. But when the sun runs out of fuel at its centre, it will contract. It will burn helium into carbon, nitrogen, and oxygen. But when it runs out of fuel, stars reach a small size and then stop. And the biggest stars, nothing will stop their collapse. There's no force known in nature that stops them from collapsing to a point. And so most of the black holes in the universe are formed in the death of stars. But the big black holes that live at the centre of galaxies, we don't know exactly how they're formed, but they appear to begin their life pretty early on in the evolution of the universe and grow up around the galaxies themselves.
Okay, he's inside. He goes beyond the event horizon. He's inside this black hole. I mean, can you even be inside a black hole? Is that a nonsense?
In principle, yes. So when he gets inside of it, he finds this tesseract, and so I mean that's a little bit more playful. There's a lot of, from the outside, there's a saying that black holes have no hair, that we can't tell what a black hole was made of. It has, no memory of what happened inside of it. But once you got inside of a black hole, complicated things happen to time. In particular, he's able to reach back into his own past and send messages. So that part of it, in some sense, is clearly fanciful, but the movie is playing, I think, with the sense that, as we sit outside of the black hole, we have no knowledge of what's going on inside of it, which means, in some sense, that pretty much anything can happen inside of a black hole. Because
what would be inside most black holes would be the remains of a star? Might that still be too hot for anything to survive inside it?
That's possible. Mathematically, the thing that lives inside of a black hole is the singularity. In some sense, mathematically speaking, the black hole has no mass everywhere in the space-time other than the point at their centre is nothing. It's vacuum. And so, a black hole is almost a memory of where material was in the universe. It's almost like a belly button in the fabric of space that's been sort of knotted off as the star collapses and then effectively drops out of our universe. The fact that you've chased the remnants of this material over the event horizon, once you get into the black hole, then you would expect to see, in some sense, the remnants of whatever it was that had produced it.
Okay, right.
But that's complex.
Yes. Well, but not only does Mr. McConaughey, or astronaut Cooper, survive, he has to eject from his spacecraft, but there he is. He's not getting crushed. He's inside the black hole, and he discovers that other beings got there first and created a tesseract. Now, you said that word. What is a tesseract?
A tesseract is the four-dimensional equivalent of a cube. So again, the movie is playing with the idea that conventionally we think space has three dimensions. We can go forward and back, we can go left to right, we can go up and down. And so if one of the things that falls out of Einstein's theory in some sense is that there are ways of looking at it that makes you think that space may have extra dimensions that are somehow folded up most of the time in ways that allow, that we can't perceive either with our natural senses or with machines. But if you get into very extreme environments, they may unpack to some extent. And so again, there's a level of playfulness in the movie, and it's pulling apart some of those ideas. There's also a wormhole in the movie, which again is something that maybe makes more sense.
I was throwing up whether to mention that or not, because what's the difference between, now you brought it up, what's the difference between a wormhole and a black hole?
So a black hole, well, two differences. Firstly, black holes are things that we have every reason to believe exist in the physical universe. And so, up until the 1960s, I think, or even beyond that, there was a lot of debate among scientists as to whether black holes were mathematical curiosities or whether they were things that could actually, astrophysically exist. And, the evidence for that, there's been Nobel Prizes for the people who proved that the universe really does contain black holes. A wormhole, on the other hand, is again a solution to Einstein's equations, but it appears to require material that has essentially negative mass. So a stable, what we call a traversable wormhole, one you could fly a spaceship through, they don't appear to be things that would exist in our universe because they require, we can design them, but we can't, we can never find the material we would need to build one. And so they're things that exist mathematically, but not apparently things that exist in reality.
Now, getting back to Cooper inside the event, beyond the event horizon of the black hole that is gargantuan. Now, he's okay. There's the tesseract is there. It allows him to communicate through space and time with the past. He's talking to his daughter, communicating with his daughter. He's not talking to her. I think, in fact, doesn't he use gravity to communicate, to send a sort of Morse code, if I remember rightly?
Does he leave messages in sand or little or in the dust in a house that they're in or something?
Or something also that
reaches
moves
back
as
into
the
her
watch.
childhood.
It moves the hand, the second hand on the watch, I think, that she is holding.
There's a and so that part of that they're playing with there is that time flows more slowly as you approach a black hole. So he arrives back on Earth. Not a huge amount of time we're really giving everything away now. Not a huge amount of time has elapsed for him. But his daughter is an old lady when he gets home.
She's about to kick the bucket.
Yeah, and she's pleased to see him, but also you get the impression a little grumpy maybe.
Yeah. What took you so long?
Exactly.
Actually, but here's my question, and that is, well, he got out, and so did those beings, I assume, who left the Tesseract there. Now, if not even light can escape the event horizon of a black hole, how could anything with mass escape a black hole? Isn't that where it all really falls down? I was thinking about this the other day.
Yeah,
actually.
no, I think you've got them there. I think that's something that Hollywood needs for its story. But once you've gone in, you're not coming out. I mean, it's famously you can perform the experiment, but you can never publish the results. Seems to be the rule with the black hole. You can go in, but you can't come out again.
Now, Gargantuan is a supermassive black hole. Now, why is it that something bigger is more likely to be survivable than something which spaghettification happens in not such massive black holes? That seems counterintuitive to me. Can you explain that?
So it's really to do with it's to do with tides. The reason there are tides on the Earth is that the moon, the gravitational field of the moon is different, or the sun on the near side and the far side of the Earth. And so the larger the black hole, the more slowly the gravitational field of the black hole varies as you move through space. And so a very small black hole has a very kind of sharp, steep gravitational well, as we call it, whereas a large black hole, the same depth, where you reach the point where you would need to travel faster than the speed of light to get away, the curvature of the gravitational well isn't as steep in terms of how sharp it is as you move away from it, and that means that all of you is accelerating at pretty much the same speed, as opposed to, as I was saying before, if one part of you is being pulled at a much greater extent than the other, then eventually you're going to stretch in a very painful way.
Right. So that's stretching, and that stretching, it is, it's not something that somebody observing, a third party would observe the person being stretched, and even the person inside the body being stretched would see, hang on, my head's way up here and I can't see my feet anymore and it hurts.
Exactly. No, there are some tricks of perspective and relativity, which means, my clock might run slower than your clock, and, but we both, everything is self-consistent for us. If your feet are being stretched relative to your head, you'll notice that. It's not something that you can explain away as a result of two different perspectives. It's a real thing.
Sorry to come back to this, Easther, but why is it that the gravity might not necessarily crush you?
So gravity doesn't crush, and it's more that it stretches. It would crush you if the black hole had a solid surface and you wound up on it. Then you would be smeared on the surface of the black hole. But
if you're in a vacuum, no, not a problem.
Exactly, and so the surface of the black hole isn't, there's nothing that's kind of painted on space, if you like, to tell you that, you've crossed from one side of the line to the other. And so in principle, you could, if it was a very, very big black hole, you could make your way across the event horizon without really noticing that it was there. If you looked out at the stars, at the rest of the universe, you would absolutely see that things looked very different once you were close to the black hole. But as long as you didn't open a window, you may not realize what had happened.
Getting back to more than three dimensions, do we live in a four-dimensional world in your opinion, because time is a dimension as well?
So that's the language of relativity. I mean, time is a different dimension because we can't travel backwards in it. And so from the relativistic perspective, we're always traveling through time, although we can be stationary in space. So we travel through time at the rate of 1 second per second. And so time is not, it doesn't enter the theory on exactly the same footing as the three space dimensions, but you carry them around together and you operate on, things. The description of nature is naturally four-dimensional in relativity, but with the caveat that the time you can always tell which one's the time in some sense.
Is the idea of more than 4 dimensions more than just a mathematical curiosity? Is it likely that such dimensions have to exist in order for us to explain the universe as it is?
That's a good question. It's certainly true that relativity has encouraged people to speculate that might be true. So there were actually just sort of around the time relativity was being invented, but certainly in the 1920s, this was something that was discussed in a fair bit of detail by physicists called Kaluza and Klein. And string theory, which a lot of people have heard of, is something that, and it's kind of, I was going to say simplest form, may not be quite the right word for it, but it's
an oxymoron on that one.
Its natural form seems to be that it makes the most sense in 10 dimensions, so 9 plus 1. And so that would imply that there were these 6 extra dimensions that are somehow very tightly curled up on themselves, but may unravel in the vicinity of a black hole. Whether or not that's true, we don't know. It's a hypothesis rather than something we're sure about. But it certainly becomes a possibility in a way that it wasn't previously, I think is probably the right way to say it.
Okay, I'm going to throw this out at you now, and that is, if it was truly possible for somebody to use a tesseract to communicate through space and time with the past from the future, as it happens in Interstellar, maybe if such things already exist, could it explain? Is it a theory to explain apparitions or ghosts or anything like that?
It is in the movie, but not necessarily in real life. I strongly suspect.
You don't think we ever come across? Without knowing it, come across a blip that's created from another dimension?
Me? No, I don't.
It seems possible that whatever beings went in there, or whether they sent machines in to make the Tesseract, could have stayed, and he could too. And that could have been the end of the story, and thoroughly convincingly.
Yeah, I think, the story behind the movie is that a well-known physicist, Kip Thorne, who again, a Nobel Prize winner eventually, did a lot of the mathematical modeling so that the images that you see of the black hole in the movie are as realistic as pretty much as they knew how to make them. They changed a couple of things for dramatic effect, but very little. I think from a drama point of view, I think it would have been better to leave him there. But from a movie point of view,
they wanted a happy ending.
It's Hollywood, right? And
he promised his daughter he would come back.
And like when a dad promises their child they're going to do something, like laws of physics,
they've got to do it, especially in Hollywood.
There's no excuse, right? You've got to follow through.
That's right. Thanks for listening to this episode of Sci-Fi Sci-Fact, hosted by me, Brian Crump, produced by Andrew Robertson, and of course, made possible thanks to the incredible knowledge of those brilliant scientists at the MacDiarmid Institute. You can find more episodes of Sci-Fi Sci-Fact on the RNZ Podcasts page. RNZ Podcasts are also available on Apple Podcasts, Spotify, iHeartRadio, or pretty much wherever you might find your podcasts. And make sure to follow us so you don't miss out on any new episodes.